Hi everyone. So today's video is going to be probably a shorter video where we're just going to do some more examples of L'Hopital's rule. I just wanted to point out a couple of kind of slightly more complicated things that can happen when you're using L'Hopital's rule, and then we'll see one other kind of situation where you can use L'Hopital's rule, basically when you have something that's called an indeterminate product. So before we get into that, I just want to remind you of what L'Hopital's rule says. So basically what we talked about in yesterday's video is that there are certain situations where if you're taking the limit of a fraction of two functions, sometimes you can just tell what the answer is based on what's going on in the numerator and what's going on in the denominator. However, there are some situations like where the numerator and denominator are both going to positive or negative infinity, or where the numerator and denominator are both going to 0. Then that's what's called an indeterminate limit. And so what you need to do is use this rule called L'Hopital's rule. So when finding the limit as x approaches a, and as I mentioned in yesterday's video, a in this situation could be either a number or it could be plus or minus infinity. So when you're finding a limit and there's kind of two different situations. One is if the limit of the numerator is equal to plus or minus infinity, and the limit of the denominator is also equal to plus or minus infinity. And by the way, they don't need to equal the same type of infinity, right? You could have the numerator could be going to plus infinity, the denominator could be going to minus infinity, or vice versa. It doesn't really, that part doesn't matter, as long as both of them are going to some sort of positive or negative infinity. And so if that is the situation, then this is sometimes referred to as indeterminate type infinity over infinity. And then the other type of situation you can have is where the limit of the numerator and the limit of the denominator are both 0. So in this case, I'm saying they're the same because they're both 0, whereas in the top one of them could be plus and one could be minus. So that's why in the top, I wrote them out separately. So this is what's called indeterminate type 0 over 0. So if one of those two things happen, then the limit as x approaches a of f of x over g of x is the same thing as the limit as x approaches a of f prime of x over g prime of x. So basically what this rule says is that rather than taking the limit of the original two functions in a fraction, you can instead take the limit of their derivatives in a fraction. And one thing I mentioned in yesterday's video that I just want to point out again is that you're not using the quotient rule here. And the reason that you don't have to use the quotient rule is because you're not taking the derivative of this whole function. What you're doing is you're taking the derivative separately of the numerator and the denominator. And the reasoning behind that I mentioned in yesterday's video is that you can kind of think of it as like when you're taking a limit of a fraction of two functions, you can kind of think of it as like a race between those two functions, or like a battle, right? They're kind of battling it out to see which one of them is really going to kind of like control where the answer ends up. And so one way to think of like, why are we taking the derivatives? Well, you're kind of comparing which one of these two functions is growing faster, because whichever one is growing faster is going to be the one that kind of takes control in a sense. And that idea makes a little bit more sense when we're talking about limits at infinity versus when we're talking about limits at a number, but I think that same kind of general idea still makes sense. Okay, so I want to start by doing an example, and I would encourage you to try this example yourself, and that probably goes for all the examples in this video, but we're going to do the limit as x approaches infinity of x over ln of x. So I'd encourage you to pause this, try it yourself, and then come back and we'll talk about it together. So first thing you always want to do when you're faced with any kind of limit, and especially this is going to be true like on the final exam, I'm going to give you a variety of limits and they're going to be kind of mixed together. It's not going to be like, here's all the L'Hopital limits. It's going to be a blend of different types of limits. And so you have to decide, can I use L'Hopitals in this case or not? And so how do you decide that? Well, you take the limit of the numerator and the denominator individually first and verify that you have one of these two different situations. If you don't, then you can't use L'Hopital's rule. So in this case, the limit as x approaches infinity of the numerator is infinity, and the limit as x approaches infinity of the denominator is also infinity. So I mentioned, by the way, the limit of ln of x, that's one of the things we talked about in yesterday's video. So that's a good one to kind of just be familiar with. So we have infinity over infinity as our type of limit, and so that means we can use L'Hopital's rule. And so we're now taking the limit as x approaches infinity of the derivative of x divided by the derivative of ln of x. So what is the derivative of x? Well, that's just equal to 1. And what's the derivative of ln of x? That's 1 over x. So if you were to try to then evaluate the limit from this point, the limit of the numerator would just be 1, right? And then the limit of the denominator would be 0, right? Because the limit as x approaches infinity of 1 over x is 0. And 1 over 0 is undefined, so that doesn't really help us. So what you can do, and this is kind of the point of me showing you this example, is that after you take the derivative, now you're just faced with a new limit. So you can do whatever you want with this limit. Anything that you can validly do to a limit, you're allowed to do in this case. Like you can forget about the derivatives, forget about the original function, really just focus on the limit that you're looking at right now. So if you were just faced with this limit in general, you might notice, well, I can actually simplify this fraction, right? 1 over x is the same thing as 1 times x over 1, which is just x, right? So all we're doing is we're just kind of taking this and we're simplifying it. So that's another thing that you should be on the lookout for when you're doing L'Hopital's rule is after you take the derivative, take a pause for a moment and see, can I simplify this? And if you can, then do that, because that will probably help you get to your answer possibly sooner. So what do you get here? You have the limit as x approaches infinity of x, and that is equal to infinity. Okay, so I want to do a couple more examples. So let me go to another page. So let's try now the limit as x approaches infinity of 5x squared over e to the x. So first we want to verify that this is a L'Hopital's rule problem. So we want to take the limit of the numerator and the denominator individually first. So the limit as x approaches infinity of 5x squared, that is infinity. And the limit as x approaches infinity of e to the x is also infinity. So that tells us that we have a type where we are allowed to use L'Hopital's rule. So we're going to take the limit as x approaches infinity of 5x squared, take the derivative of that, and then e to the x, take the derivative of that. So what happens when we take the derivative? Well, we get 10x in the numerator, and we still have e to the x in the denominator. So if we now try to take the limit, if we think, what's the limit as x approaches infinity of 10x? Well, that's still infinity. And the limit as x approaches infinity of e to the x, that's also still infinity. And so that tells us that this is still indeterminate. And so what are we going to do? We're going to use L'Hopital's rule again. You can use L'Hopital's rule as many times as you want. Every time you kind of finish using it, you want to check in again and see like what's the situation now. And if it's still indeterminate, you can totally just use the rule again. So we're going to take the derivative now of 10x and the derivative of e to the x again. And so now we're going to get 10 over e to the x. And so now we're in a situation that we discussed in yesterday's video, where if you have the numerator just being a number and the denominator is going to infinity, then you can conclude that your limit is 0. Because basically you're going to get these really tiny fractions, right? Like 10 over a billion is a really tiny fraction, really close to 0. All right, let's do another one. Oh, and before I move on from this, I just want to say that, the same thing would have worked if this was like 5x cubed, right? Then we would have had to use L'Hopital's rule actually 3 times. Or if this was 5x to the 7th, we would have to use L'Hopital's rule 7 times. But regardless, one thing you might notice from this is that no matter how high this exponent is, it's still eventually going to go down to being just a number if you take the derivative enough times. Whereas e to the x, as many times as you take the derivative, it's still e to the x. So if you think of these limits as being kind of like a battle between the numerator and the denominator, basically the denominator is always going to win if it's e to the x. E to the x is going to beat any x to a power. Even if this was like x to the 100th power, I wouldn't ask you to do that because you'd have to take 100 derivatives, but still the e to the x would eventually win out. All right, another example here. So now let's do, and again, I would encourage you to pause the video and try this yourself. So the limit as x approaches infinity of sine of x over x squared. So this is actually kind of a trick question. It's not really a trick question, but this we'll see is actually not a L'Hopital's question. So how do I know that this is not a L'Hopital's question? Well, the limit as x approaches infinity of sine of x, what is that? Well, let's think about what the graph of sine of x looks like. Sine of x goes back and forth, right? It looks like this. And it keeps doing that forever and ever and ever. And so the limit as x approaches infinity of sine of x does not exist, because the graph doesn't, like, when we're talking about limits at infinity, we're looking for the graph to either go up and up and up and up, or down and down and down and down, or for it to kind of flatten out to a particular level. And none of those things happen with sine of x. Sine of x just kind of goes back and forth and back and forth. So the limit does not exist. Whereas the limit as x approaches infinity of x squared is equal to infinity. And so this tells us that we cannot use L'Hopital's. And I actually have many times put a really similar question to this on the final exam for this class. And I would say more than half of people kind of fall for it and try to use L'Hopital's rule. But just really make sure that what you're doing makes sense. The limit as x approaches infinity of sine of x is not infinity. That would require that the graph gets bigger as x gets bigger, and that just doesn't happen. So what we want to do instead in this case is actually use the squeeze theorem. So how do we know to use the squeeze theorem? Well, basically when you have limits that involve sine or cosine, where you can't use L'Hopital's rule, you can't simplify it, that's what should kind of point you to maybe using the squeeze theorem. So how does the squeeze theorem work? Well, we need to figure out two functions that this function is in between. So we can start off by saying that we know that, and maybe let me just write down that we're using the squeeze theorem. Use the squeeze theorem. So we start off by saying, okay, we know that sine of x is between -1 and 1. And so that tells us that -1 over x squared and +1 over x squared, those are kind of the boundaries of sine of x over x squared. And so what we now want to do is find the limits of those two kind of bounding functions. So the limit as x approaches infinity of -1 over x squared, well, that's equal to 0, right? That's one of the cases that we talked about in yesterday's video, where the numerator is just a number and then the denominator is going to infinity. And if we take the limit as x approaches infinity of +1 over x squared, same thing. And so basically, because these two things agree, because we got the same result for both of them, why is this called the squeeze theorem? Well, we're kind of squeezing this function in between them, right? We said that this function has to be between those two. And so if both of them are going to 0, well, that means that this one is also going to 0. So the limit as x approaches infinity of sine of x over x squared is also equal to 0. So just wanted to, I threw this in there just to kind of remind you that as nice and friendly as L'Hopital's rule is, and as tempting as it is to just kind of use it everywhere, it doesn't work in every situation. So if you tried to use the squeeze theorem here, I've seen, like I said, lots of students unsuccessfully do this. They get something like, they get cosine of x over 2x, and then maybe they do it again and they get cosine of x over 2. But then still, it just doesn't make sense, because then they end up saying that the limit as x approaches infinity of cosine of x is also infinity, and that's also not true. So it just doesn't work. Okay, so the last thing I want to talk about is something called an indeterminate product. So basically, so far what we've talked about as indeterminate limits have been limits of the form infinity over infinity or 0 over 0. But there's one other type of limit that is indeterminate. And actually, there's even more than that. And so we're just going to talk about products and the quotients that we already talked about. Just so you know, there are also indeterminate kind of like exponential expressions and also indeterminate differences, so subtracting two things. Because this quarter is shorter and everything else going on right now, I didn't want to put more on your plate than necessary. So I'm sticking with these two indeterminate forms because they're kind of like the most important and the ones that are most likely to come up in future classes. But if you're curious, if you look at this section in our book, so section 4.4, you'll see that there are other kind of situations where you can use L'Hopital's rule. Anyway, so indeterminate products are things that look like this. So if you're trying to take, or actually let me just say this. I'll say if the limit as x approaches a of f of x is equal to plus or minus infinity, and the limit as x approaches a of g of x is equal to 0, then if you try to take the limit as x approaches a of f of x times g of x is an indeterminate product. And so similarly, like when you have 0 over 0 or infinity over infinity, how those things just kind of like, you can't really decide what wins out, right? It's like, you can't make sense of the numbers you have. Similarly, when you're talking about an indeterminate product, so if you have 0 times infinity, those two things are really kind of battling against each other, and it's hard to figure out what's going to win out. So you can call that indeterminate type 0 times infinity. Or I guess the way that I wrote it, maybe I should say infinity times 0, but it doesn't matter. So when you have an indeterminate product, you can always rewrite it as an indeterminate quotient. So if you have an indeterminate product, so an indeterminate product of the form f of x times g of x, you can always rewrite it as a quotient. So what is that quotient going to look like? You can either write it as f of x over 1 over g of x, or g of x over 1 over f of x. And we'll see an example of this in a second. And what happens is if you do that, then that will actually give you either infinity over infinity or 0 over 0, kind of depending on what your functions are and which one of these two things you're doing. So that will give you indeterminate type 0 over 0 or infinity over infinity, so you can use L'Hopital's rule. oops, you can Okay, so we're going to look at a couple of examples. So the first one is going to be one where you actually don't really need to think about rewriting it like this. I think it will be like pretty clear how to rewrite it. And then we'll do an example where you do need to kind of maybe think a little bit harder about how to rewrite it. So the first example I want to look at is the limit as x approaches infinity of e to the negative x times x cubed. So why is this an indeterminate product? Well, if you tried to take the limit as x approaches infinity of e to the negative x, that would be like the same, doing the same thing as the limit as x approaches negative infinity of e to the x, right? Where that would be thinking about like what happens when you're plugging in like negative 1,000, negative 1,000,000 to e to the x. And so if you think about the shape of the graph, that limit is going to be 0. And then if you take the limit as x approaches infinity of x cubed, that would be infinity. So this is going to be a type 0 times infinity. And so in this case, you could like kind of use this idea and rewrite it, but really I think you can maybe see how to rewrite this as a fraction already, right? So e to the negative x is the same as 1 over e to the x, right? So we can rewrite this instead as the limit as x approaches infinity of x cubed over e to the x. And so now we have an indeterminate of type infinity over infinity. And now we can use L'Hopital's rule. So you're not allowed to start taking derivatives until you actually have your limit written as a fraction. So how does this work? Well, we take the derivative of the top and the derivative of the bottom. And so this is kind of like one we did earlier. So the derivative of the numerator is 3x squared, and the derivative of the denominator is e to the x. And so now we still have type infinity over infinity, right? Because if you take the limit of 3x squared and the limit of e to the x, those are both infinity. So we have to use L'Hopital's rule again. And now we get the limit as x approaches infinity of 6x over e to the x. And again, we still have infinity over infinity as our type of limit. And so we want to take the derivative again. And so now we have the limit as x approaches infinity of 6 over e to the x. And so now we can finally say, okay, we have a number over something going to infinity, and so that's going to be equal to 0. And you might say, well, can't you tell that that's going to happen earlier on? Like, you know, if you can tell that like the denominator is e to the x, the numerator is x to a power, you know, shouldn't you be able to tell the answer is going to be 0? And the answer is yes. But like I mentioned in yesterday's video, I do want you to kind of go through this process of really kind of proving for sure that the limit is what we're claiming it, or what you think it's going to be. So by the way, this does kind of fit with this idea up here, because basically what we did, so if you rewrote this function as x cubed over 1 over e to the negative x, 1 over e to the negative x is the same thing as e to the x. But that's kind of like a roundabout way of getting there, because, you know, just seeing the negative exponent should tell you, okay, I could put that in the denominator. But next we're going to do an example where you really do have to kind of force your function to look like one of these two up here. So this is the last example we're going to do in this video. So I want to do the limit as x approaches 0 from the right of x times ln of x. Oops. ln of x. Okay, so this is a product, right? There's no kind of fraction to be seen, but the derivative, or sorry, the limit of x would be 0. And then the limit as x approaches 0 from the right of ln of x is negative infinity. So maybe let me write that down, because that's one that maybe you were a little less familiar with. We talked about it yesterday. But so that tells us that we have, again, a 0 times infinity type. Oops, of ln of x. And so this tells us that we have a limit of the type 0 times infinity. And I know it's negative infinity, but that's why, like, when we're talking about these types, you're not saying literally like what the limit's equal to. It's just kind of a label for that kind of like format of a limit. So we want to find a way to rewrite this. And we kind of have two choices. And I'm going to write both of them down, but really only one of them is going to be kind of the more useful one. So we have two choices. We could either rewrite this as ln of x over 1 over x, right? That's the same thing as x times ln of x. Or we could rewrite it as x over 1 over ln of x. So what makes me say that this one is better? Well, basically, remember that we're going to be using L'Hopital's rule, so we're going to be taking derivatives. And so the derivative of ln of x is going to be 1 over x. And so we're going to have like these two different parts that actually interact pretty well with each other, right? ln of x, take the derivative, you'll get 1 over x. Take the derivative of 1 over x down here, and you'll get negative 1 over x squared. And so those are things that can be kind of combined and simplified. Whereas if we tried to do it with this one, well, taking the derivative of 1 over ln of x, that's not so friendly. That's going to be like a chain rule or a quotient rule. And so that's still going to have an ln in it. And it's basically just going to get more complicated when you take the derivative. And so this one is, sure, it is true that this limit is the same as our initial limit, but it's just not going to be, it's basically harder to work with. And it's fine when you're doing these, sometimes you'll do it the wrong way first and you'll just realize, okay, I'm taking the derivative, it's not getting me anywhere. That tells me that maybe I should try it the other way. Okay, so let's work with this other way of writing it. So the limit as x approaches 0 from the right of, and now we're going to take the derivative of ln of x, and we're going to take the derivative of 1 over x. And so this example actually was on your worksheet from yesterday. I didn't give it to you in its original form. I gave it to you like this, but this might feel a little familiar. So now we have the limit as x approaches 0 from the right of 1 over x is the derivative of ln of x. And then the derivative of 1 over x is negative 1 over x squared. So I think this is a really good example of one, and actually, sorry, let me just go back one step and go back to here for a second, because I didn't verify the fact that this is type infinity over infinity or 0 over 0. So the derivative of the numerator here would be, the limit of the numerator would be negative infinity. And then the limit as x approaches 0 of 1 over x, well, that's infinity. Just think about what the graph of 1 over x looks like, or think about what happens if you plug in numbers that are like just above 0. If you do 1 divided by like 0.001, you're going to get a big number. And so this is a type infinity over infinity. Okay, so we could use L'Hopital's rule, and then when we get down here, I think this is a really good example of one where simplifying makes all the difference. So you might look at this one and say, okay, well, the limit of the numerator is infinity, and the limit of the denominator is negative infinity, and so I should just use L'Hopital's rule again. And you could do that, but it really doesn't help you because you're just going to kind of make your functions more complicated. So instead, before taking any derivative again, you should always check, is there some kind of simplification I can do? And so in this case, we can rewrite this as 1 over x times, and then the reciprocal of negative 1 over x squared would be negative x squared over 1. And so that simplifies to the limit as x approaches 0 from the right of negative x, right? Because we have x squared, we have x in the denominator, and so we're left with negative x. And so anytime you're taking the limit as x approaches 0, if it's from the left or the right, doesn't matter, of x, positive or negative, your answer is always going to be 0. All right, so that's it. And we're not really going to get any more complicated than this. And honestly, I think the examples on your homework are probably even a little easier than some of these. But like I said, if you're interested in kind of delving into more stuff, feel free to look in the book. And if you have any questions for me about that, I'm happy to answer them. All right, I will see you all next time.